Today I was preparing for a video to outline timing of brush motors, direction of rotation of brush motors, and I killed the power supply, digital power supply, that 0 to 30 volt 10 amp adjustable voltage, adjustable amperage limited, and it smoked and made quite a loud noise. So I figure, since it's going to be a little bit difficult to make that video, I'll just make a video taking apart the power supply. So let's see what we find. When it failed the first time, it made a buzzing noise and popped the fuse quite spectacularly. Actually broke the fuse into a few pieces. And so I replaced the fuse, thinking maybe that was the loud pop that I heard. And it turns out, no, that was not it. When I powered it on the second time, there was a very strong 60 hertz buzzing. It sounded like an electric arc coming from the inside, and a much larger billow of smoke. Nasty, nasty billow. So let's see if there's any obvious telltale signs. I can smell it. But I can't see anything. Interesting. So far, no sign of damage. Smells like up here. I suppose we'll just need to take off the heat sink, the heat spreader. Curious that there was quite a large amount of smoke that came out of this, but no sign of failure. Maybe it was the fuse again that just let out all the smoke, but it really seemed that it was from somewhere in here in the case. Well, you see some evidence. Very fiddly assembly. There we are. So, we have these MOSFETs here and here that control the switching. I'm assuming. Let's look. And you always want to make sure the big caps are discharged. It's always a good idea. Let's see. Should be good. Alright, so this component, you can see the burning. Unhook the display. Well, we can't read what it is anymore. The one next to it looks like a Fairchild 1A26PT or 12N50T. Well, one might assume that it is the same component that fried, but you know what happens when you make assumptions. So I'm going to do a little research and see if I can come up with any hits and try to replace this guy. Thanks for tuning in so far to the dissection of a failed digital power supply. Okay, so I've done some research on the schematic of the circuit, a little bit of reverse engineering, a very simplified schematic, but did a little bit of research online, and between looking at the circuit itself of the power supply that went up in smoke and the data sheets of some of the parts, turns out that the switching MOSFET that exploded, which I believe it would be the negative side, it was also the same as the positive side, Fairchild 12N50T MOSFET. And they actually do have integrated body diodes on them, I think, the way that I drew it. Let's see, this may be reverse biased, but whatever, you get the idea. They do have integrated reverse protection diodes built into them. And so what I was wondering was whether or not this was a reverse bias issue that caused it to pop, or whether it was a timing issue. And since this MOSFET has an integrated body diode, it should not have exploded from just a simple reverse voltage going through. So what likely happened was that as I was adjusting the voltage up and down on the controller, the inductance of the motor, which was pretty nasty, a very high inductive value on the motor, the inductance caused the switching circuitry to get out of sync. So there's more circuitry beyond this, and there's a lot of control circuitry pretty much at every stage of here. There's sense resistors and little ICs connected to it, but this is a fairly simplified circuit, so you can at least see what's going on. At any rate, what seemed to have happened was that the switching got out of sync, and this guy essentially was presented with a dead short across it, and it just exploded. The first time. The second time, it caught on fire with a very nice 60 hertz buzz to it and showered the PCB with plastic and metal bits. But the basic way that the voltage regulator works is as follows. We have our ground source, and then we have 120 volt AC here in the US at 60 hertz. 60 hertz. Can't even read that. Whatever. Here we go. 60 hertz. And so the 60 hertz comes in through a 1-to-1 transformer really just for isolation purposes. And so it goes across the transformer, does not change in voltage. And then the secondary side of the transformer is connected to ground on one side, the opposite side of this rectifier bridge, and then the primary side is also connected in as well. So this is kind of an isolation circuit here. We have ourselves a capacitor for isolation reasons as well. So it goes through this rectifier bridge and comes out the other side as DC voltage. 175 DC is about what 120 volt AC gets rectified to. Now, the reason why they did this is so that they could use two back-to-back MOSFETs. There's a certain name for this kind of daisy chaining, but at any rate, they're back-to-back so that one side will switch to positive out of the emitter, and then the other side will switch to effectively the negative of MOSFET number one. So what this allows is that you can use your positive and negative rails coming out of the rectifier to create another AC waveform. And so these take turns going back and forth, changing the DC back to AC. The reason why you would want to do this is so that you can switch much faster than your mains. So, there's going to be large capacitors. There's some really large capacitors inside to smooth this to a nice, a steady DC coming through. So, it would be like 175 for our DC on there, 0 volts. And then what it does is it takes it and switches it back to essentially 120 volt AC. But it can do it at a far, far higher rate. We're probably talking about, 10K, 20K, maybe even in the megahertz range. I didn't have a chance to put an oscilloscope on this. But the reason for doing this is that your transformer size is directly connected to your switching frequency. So a 60 hertz transformer is going to be far larger than, say, a 10 kilohertz for the same power output, and it's because of the time that it takes to switch. There's a lot of switching losses involved. There's a lot of back and forth. So let's say we have this and we convert it into AC again. We'll put the AC 0 there. So as we're going up and down, up and down, up and down on this AC waveform, there's a lot of time spent, if this was 60 hertz, let's say. There's a lot of time spent charging up capacitors and discharging capacitors and charging up capacitors and discharging capacitors back and forth. And there's a lot of time conducting. And so your total amperage swing, or the amperage ripple, will be much higher in this 60 hertz transformer. Whereas in a, let's just call it, 600 hertz transformer, so it would have 10 times the up and down. And, this would be a fairly, that's not 10 times, but it would be a very fast spike up and down. And so there's not nearly as much time for the components to react. There's inductance on everything, and inductance will try to prevent changes in voltages and amperages. So what you get out of a faster switching frequency is far less amperage ripple on there, and since your amperage ripple is less, there's less resistive losses in the circuit, and you can get away with a much smaller transformer as long as it can still handle the total power. Normally would be limited by the wire size on the transformer and the efficiency of your core, because there's switching losses in the core, of course. And the faster frequency that you switch, the more core losses, so you have to offset that with thinner laminations, and it's kind of a rabbit hole where you change one thing and then other things have to change to suit. But at any rate, the circuit is switched by these two transistors at a much higher frequency than the wall, so that they can get away with a very small transformer to step this down to 30 volts. And it's far more complicated, as I stated. There's multiple transformers inside, but it's the transistors that's right off of essentially the worker transformer, where we're taking 175 on this side and we're converting it down to 30 volts on this side. So it's going to have a ratio of 175 divided by 30 in the left and right hand turns. So I would like to replace this transistor because it was a fairly expensive power supply, but you can't just throw any old transistor in there. The original one, these were 12 4150T, made by Fairchild, if I'm not mistaken. It's a TO220 package. TO220 package. Originally, that's what was used in speed controllers for the RC car world. It's a very ubiquitous package for aerospace, for the automotive industry. Obviously ubiquitous enough that it was inside this power supply. Now, there are many options for TO220s, but we have to make sure that it has the same voltage rating. These were 500 volts, and we need to make sure that it has the same amperage rating or better, which was 11.5 amps on these little packages. That's really not a whole lot, but when we consider this transformer here, if we're pulling 10 amps off of this side, then it's going to be roughly 20 times or so. Let's see, 5 times. It's going to be roughly 5 times less. So 10 amps on this side would be only 2 amps on this side. So they overrated the transistors. Now, what is also important is the switching speed of this. This is the gate where you would apply a positive voltage, because these are in-channel, usually denoted right there, in-channel transistors. So you pull this high to a positive. Usually, I believe these were switchable up to 30 volts, and it probably triggers somewhere around 5 volts. So you add, like 7 to 12 volts. The more voltage, the faster the turn-on rate. So you pull these gates high, and they turn on. But what we need to make sure is that the gate charge is not much more than the original component. And these actually had a gate charge of 22 nanocoulombs. 22 nanocoulombs. And so if you know the voltage that you're driving your gate, if you know the charge of your gate, and then if you know the resistance of the components themselves that are driving the gate, you can backwards extrapolate the amperage, multiply by your voltage and time, and you can get your gate charge time. Now, we'll do another little graph here. When a transistor turns on, we want it to be a perfect on and off. Any time that is spent switching on or switching off is in a conductive, resistive region, I should say, of the MOSFET or the transistor. And in reality, when you switch one on, there's going to be a little bit of slew. It takes a little bit of time to charge up these gates, and it takes a little bit of time to turn them off. So it ends up being a sloped on-off cycle, and then this area right here is your switching losses. And usually this is just basically heat that would be generated while the MOSFETs are turning on and off. And since we have 2 of them back to back, we can't have them turned on at the same time, or just short circuits the whole thing. That's not good. So we have to time the on and the off between component 1 and component 2 and have dead time between them. So if we increased our gate charge by swapping in a more powerful MOSFET, usually a higher amperage or higher voltage rating will make that gate charge go up, then we would screw around with this slew rate. And so if we used something that had a much larger gate charge to it, it's going to take a really long time. It may not even get all the way into the conductive region, so the slew is going to be far, far worse, and it may run into the other side switching on, and then we would have a period of time where there is, essentially from here to here would become a dead short across them. So I can't just slap in any old transistor to fix this. The one that I would love to use is one that I'm very familiar with. It is made by, I'm so familiar, I can't even remember right now. It's the 4110 FET made by IR. And it's only rated for 100 volts, though, so we can't use this. Obviously, we've got a 175-volt rail DC coming in here, so we can't throw in a 100-volt transistor or MOSFET. However, just by comparing these two, the 4110, and it's usually, IRF B4110, and then they'll have like a PBF on the end, which stands for lead-free version. At any rate, these guys, so they're far less rated, only 100 volt, but a whopping 120 amps instead of just 11. These guys over here, same package, the TO220. This is 11.5 amp for that guy. 120 amps for this guy, but the gate charge is about 150 or so, I think. 150 nanocoulomb gate charge for the 4110 FET. So to turn it on, it would literally be, let's see, oh, that's about 20. That's about so what's about 8 times the time to turn it on, or so, 7 to 8 times the amount of time to turn this on, which is a huge change to the circuit. So as much as I would like to just find a high amperage rated transistor to throw into the circuit, it would mess up all the rest of the circuitry. And so what I'm going to have to do is either find an exact replacement, the 12N50T, throw it into the circuit, and hope that nothing else was damaged when it exploded. Or I'll have to find a very similar one, has to have a very similar gate charge to it, has to be rated at least 200 volts DC, but because of ripple, I would probably want to rate it around 400, and because of the components that we buy, you can only buy what's offered, that is essentially going to be a 500 volt transistor or MOSFET. So I'm kind of stuck with using the components that are in there. I may find something else in this package that has, maybe a little bit higher amperage rating, but it's probably going to have a little higher gate charge, and the risk of putting that in for, cooler running just really isn't worth it when it boils down to it. So next thing for me on this is going to be locating and purchasing a new MOSFET for the lower side of the channel, and putting it in and giving it a shot. And the next time I go to turn this one on, you can bet that I will have a video recorder on there, have a camera recording, because the initial failure was pretty spectacular. And the second failure, when I turned it on again, was even more so. Felt the wave of air coming out of the box on my hand, because like a dummy, I, of course, picked up the power supply the second time that I turned it on and was holding it in my hand. I'm fortunate that there wasn't an issue where it was shorted to ground, where I could become live, and if I was also grounded, then it would have gone through my body. So next time I'll have it on a camera, and I won't be touching it when I turn it on, and we'll just throw in a new MOSFET and see how it goes. So thanks for tuning in to this accidental episode here, but hope you learned something.